In this video, I will explain how to train very deep convolutional neural network models using residual connections. So I'm going to start by importing all the libraries. And then the next thing I'm going to do is load the MNIST dataset into training images and training labels, test images, and test labels. Let's visualize a random image to see how it looks like. So the image is 1 and the label is 1. Now, for the purpose of speed, what I'm going to do is only use the test images as my training images because it only has 10,000 images and 10,000 labels. That's going to speed up the training process and evaluation process and so on. So we also normalize the images, divide by 255, and then we convert to two categorical, the labels to two categories, two categorical. So now after this, my training input features and the labels are ready to be fed into a deep learning model. The first case that we would like to look at is design a fully convolutional network. And we'll see that at depth 16, it doesn't do much of a learning. Or even if it does, like, as we increase the depth, it's going to stop learning. So we have this input image of size 120 by 120 by 1, and then we take these image as input, apply conv2d, input image, apply conv2d, and then here's our output 1. And then we feed our output 1 to conv2d. What comes out is output 2, and then I'm going to set output 1 to output 2 to output 1. So it's going to be a linear stacking of convolutional layers, and then we finally flatten out, add some dense layers, and then create the model. So let's compile the model and print model summary. And then after this, we're going to do the plot model to see how visually the model looks like. So I'm going to do plot model, and let's scroll up all the way at the beginning. What we see is here's our input layer, and then the next conv2d layer. So the whole input gets fed to the next layer with 16 filters, and so on. So this is a linear stacking of convolutional layers. So let's run model.fit to see if it does the learning. Sometimes even at depth 16, you see that the models do learning, but many times at higher depths, more than 16, 24, and so on, the training process, the deep convolutional models do not actually do a good bit of learning. So let's wait for the first epoch to complete and see whether the model does any learning or not. So here's our first epoch running. We see that the accuracy on the training set is around 10%. Okay, so the validation data, the accuracy is 11.5%. The second epoch is running. Now remember, this is all in a GPU, and yet we have this speed. If we actually ran this on a CPU, the speed would be much lesser. So after 2 epochs, the accuracy is the same. After 3 epochs, the validation accuracy is still the same. So clearly, this model is not like in a direction to do good learning. The loss is decreasing a little bit every time, but it's actually quite far from how we would like to see the training proceed. So I'm going to stop this training here, and what I'm going to do is next take us to the next step. And in this case, what we are going to do is simply make a residual connections between these convolutional layers. So we have everything is same, input IMZ, we apply first conv2d, and then here what we do is pass the output 1, which is here the input, to a conv2d. What comes out, we add output 2 and output 1. So here's our input, and here's the output of the first layer. We add them up and create another layer, output 2, and then we make output 2 as output 1. So this is the standard way to create residual. I mean, conceptually, this is how we create residual connections. And then rest is the same. So let's build this model. And then so it should be similar number of parameters. So 210,000 parameters here. Let's see how many parameters we had in the previous model. 210,000 parameters. So same parameters, just the what's different is the way the convolutional layers are connected. Now let's do plot model to see how visually the model looks like. Now we will see that, so let's go to the top. So here's our input. We apply first conv2D, 16 filters, and then we apply another conv2D. But then since this is a residual connection, the output from this conv2D 17 layer gets added to the output of conv2D 18. So we apply convolution, we take it as it is, add them up, and then what comes out is the sum of these two outputs, the original input and the output of this convolution. So this is repeated so many times to build very deep residual network. And now let's do model.fit to see if this learns or if the loss is lower and the accuracy is higher in this case within a few epochs. So we see that the accuracy, validation accuracy, is already actually 49% in the first epoch. And then in the second epoch, we'll see that the accuracy actually it went up to 60%. So you can see that it's actually learning, it's in a direction to learn from the images much more likely or much more better than how it was in the case of non-residual or stacked convolutional layers. So in this way, I mean, we can train this for a certain number of epochs, and then we're going to get certain accuracy. But then a lot of times, what we want to do is get even higher accuracy at a cost of more resources, and even training time, right? So let's see how many epochs we have. Okay, 7 out of 8 epochs. So we're going to let this finish, but then in case of residual networks, the more you train, the very likely you're going to keep seeing increase in accuracy. So after the 8 epochs, we see that the the accuracy in the validation set is 96%. So let's leave it there. The more we train, the accuracy is going to increase. With the residual connections, the good thing is we can train even deeper models. So earlier here in this case, the model was, I think it was 16 residual connections deep, 16 convolutional layers total, 16 plus. Now let's create a model with a little bit more realistic or a practical that's commonly used resonate type architecture where one block of convolution usually is one block of residual connection is usually 2 convolutions. So I have the first convolution followed by batch norm, which is quite common. It even helps you train deeper models. And then another conv2D layer followed by another batch norm layer, and then we add the input with the output. So this is how we build a very standard residual network or residual connection. So let's build this model. Now remember, this is 32 blocks deep, but the actual number of convolutions here is 32 times 2, around 64, because in each block we have 2 convolutions, right? So here we have our model. This is 326,000 parameters, and then let's do plot model to see how it looks like. In every residual connection, we have 2 convolutional layers. So here we can see that in one residual connection we have conv2D and then batch norm followed by another conv2D and then another batch norm, and then the whole thing gets added to the input and one residual connection is formed. Okay, so now let's run history equals model.fit to do the training and see if such a model, such a deep model with so many convolutional layers can still be trained with residual connections. So in this case, even with this very deep model, we see that after epoch 1, the validation accuracy is around 60%. And in second epoch, let's see what the validation accuracy looks like. I actually originally started with the Atom optimizer for this training, and then learned that the Atom optimizer wasn't very helpful. So I changed to RMS prop, and that immediately started helping me out learning. So we do have to play around with some parameters to see what helps, what doesn't, certain times. So the second epoch is also almost done, and we can see that the accuracy is 79%. So basically, overall, we see that we can train even deeper models using residual connections.